Hello everybody and welcome to our video on section 15e, derivatives of exponential functions. First, we have a little review of y equals e to the x and y equals ln x. So just as we saw in some previous videos, the logarithm function is the inverse of the exponential function. So something like log base 2 of x has an inverse of 2 to the x. We also learned recently that the special base e to the x has an inverse of log base e to the x, and it's such an important number that we give it its own name, ln, or the natural logarithm, sometimes called ln. Okay, and if we look at the graphs, we can see a few features. For y equals e to the x, the domain is x belongs to real. X can take on any value. You can plug any value in here as an exponent on e. But the range is y belongs to real such that y is greater than 0 because there's a horizontal asymptote. The reason is there's no value, no matter what you plug in for x, you're never going to get a y that is 0 or less than 0. Okay, there's no way to make y smaller than just before 0. And the function, like all exponential functions, passes through the point 0 and 1. Also, we can see that e to the ln x equals x. That's our cancellation law. And that as we discussed, we have a horizontal asymptote at y equals 0. The ln x function here is the inverse of e to the x, so it's its reflection through the y equals x line. It has a domain where x is greater than 0 because we can remember that any inverse, we interchange the x's and y's. So here we have a vertical asymptote, and x can be anything greater than 0, but the range allows for y to be any real value, and like any logarithmic function, it passes through the point 1, 0. We have our cancellation law, and the line x equals 0 is the vertical asymptote. Now, I'm going to ask that you watch this video. I've attached it to our Google Classroom notes, and it's a good description of the number e, but also how we get its derivative. Okay, if you prefer a written description, this is the discussion taken from your textbook about where we get derivatives of exponential functions from. Essentially, if we have a function b to the x, the derivative is k times b to the x, where k is a constant that we get when we take the derivative and set it equal to 0. That's kind of a circular definition, and it comes from following this first principles definition of the derivative. Okay, I'm going to let you read that through on your own time and absorb it. I'm not going to ask you to repeat it in class. That's just to explain where this comes from. What it means is that if we can find a value of b such that the derivative evaluated at 0 equals 1, then we'll find a function that is its own derivative. And there is such a function. That function happens to be e to the x. Okay. So if f of x equals e to the x, then the derivative is also equal to e to the x. So e to the x is its own derivative, which is very exciting. Now we can differentiate composite functions involving e to the x using the chain rule. So e to the x is its own derivative, but if we have e to some function of x, then we have to take the derivative of the outside, which is just e to that function, times the derivative of the function. And we have a few examples here. So first, if we have e to the 5x, then the derivative is e to the 5x, the derivative of the outside function, times the derivative of the inside function, which is the exponent, and that's 5. So we have 5e to the 5x. We can also apply the product rule. Here we have two functions that are being multiplied together. So we take the derivative of the first function, which is 2 to the x, times the derivative of times e to the x itself, plus the derivative of e to the x, which is again e to the x, times x squared, and we can common factor out an x from both terms and an e to the x. Okay, and last we can look at this function where we take the derivative of the outside function, which is e to the 5 minus 6x plus x squared, and take the derivative of that to give us negative 6 plus 2x. I'll continue example 2 in our next video.